Another video on building blocks of geometry. This time, slightly different. We'll be talking about angles as opposed to points, lines, planes, but a very similar video than the first one that you guys had. We're just going to be talking about the properties, defining them, and then some notations and how to recognize them, how to name them, how to mark them. So first we'll start with talking about the very basic, which is an angle. So an angle is the intersection of two non-collinear rays at a common endpoint. Okay, so I have two rays here, ray AB, and I also have ray BC. Okay, they both have a common endpoint, which would be located at B. Okay. The two rays are called the sides of the angles, where that common endpoint B is going to be the vertex. Okay. Angles are always measured in degrees. We do notate an angle, so there's a way that we can use an angle notation, and that could look in one of two ways. You can either see it like that, kind of looks like a less than sign, or you can see it like that, which is a less than sign, kind of with a strike through the angle part. Technically, they do have different meanings. This is the one that should be used to name an angle. This is more directed towards the measure of an angle, but at the same time, you will see it on a lot of our worksheets, and it's acceptable to use it. So let's start naming our angles. So angles are always going to be named by their vertex. So I can very simply call this angle up here angle B. Okay, this would be no different as if I wanted to use just that symbol. Okay, or I could call this angle ABC. I could call this angle CBA. Okay, I would not be able to call this angle BCA. Okay, let's talk about why this one is not acceptable. Okay, the reason why this one's not acceptable is because of the location of this point. Okay, so notice that I said that an angle is named by its vertex. So I could call it angle B, I could call it angle ABC, I can call it angle CBA. What's important to realize is that if you're going to name it by more than just the one point, that the vertex be in the middle. So because this is angle BCA, this would imply that the endpoint, the vertex is C, which is not true. We've already identified our vertex, our common point of our rays, as being B. So this one would not be acceptable. Okay. The other way, which is probably not as common, although we do like to use it because it is an easy shortcut, is by naming it by a number. So I could also call this angle 1. Okay, we'll see later on this year that we'll be able to kind of give a number assignment to angles to be able to refer to them a little bit more easily. Okay, so acute angles, I'm sure you have heard of this before. An acute angle is an angle with a measure that is more than 0, but it has to be less than 90 degrees. So here I have two acute angles. I know they're acute because they are both more than 0, but less than 180. So I have acute angle NML, which would be the same angle as LMN. It can also be referred to as angle M. Okay, the other acute angle here in this diagram would be RQP, or angle Q, or angle PQR. But again, the acknowledgement that the vertex is the most important thing to realize when naming your angle. So then there's your obtuse angles, which are more than 90 degrees, but also less than 180 degrees. So here is an obtuse angle, because 124 would definitely fit the criteria. So we can say that angle GHI is an obtuse angle. There wouldn't necessarily be any specific markings that you would need to know for an obtuse or an acute angle, but just the recognition of where they are. So then, of course, what is that 90-degree angle? So our 90-degree angles are our right angles, okay? Right angles are most commonly marked with kind of like that perfect corner within your angle. So we could say that angle K is a right angle. Now, I tend to abbreviate, so I tend to use this for right angle, but by no means is this an exact notation that is used. Okay. Well, let's actually really quickly talk about an angle that is over, or actually an angle that is 180 degrees. It's not something that we'll refer to, but we can talk about it since we talked about a right angle. So an angle that is 180 degrees is probably most commonly known as being a line, okay? And it's a straight line, and so we'll call it a straight angle. So straight angles are equal to 180 degrees, but again, we don't often see them. Anything over 180 can be mistaken for being an acute angle as well. So there we go. So you would show it by doing the outside. And anything that is over 180 would be known as a reflex angle, something that we probably will never mention again in this course. Okay, so let's talk about a complementary angles. So complementary angles are two angles whose sum will add to 90 degrees. So in this picture, I have two acute angles, but because 38 plus 52 is equal to 90, we could describe angle LMN and angle PQR as being complementary angles. Along the same lines are supplementary angles. Supplementary angles are two angles whose sum totals 180. So because 56 plus 124 is equal to 180 degrees, I would now know that angle DEF and angle IHG would be supplementary angles. Supplementary is going to be a really important term for us. So supplementary being that they total 180. Complementary totals 90. I always like to think that it's right to give a complement. Right is 90 degrees angle. Okay, now let's talk about congruent angles. So we have seen congruence now at this point. We did see congruence with point lines, planes, and the idea is pretty much the same. Okay, so the idea that congruent means two congruent segments were two congruent segments, two segments of the same measure. Now you have two angles of the same measure. You're going to use the same exact symbol, which is the equal sign with the squiggly above it. But let's talk a little bit about how we would mark my angles. So I have an angle G here, and I have angle S here. Okay, I both have 42-degree angles, so I know that angle G is definitely congruent to angle S. I can mark my two congruent angles by very simply marking that interior of the angle. So I could just go one here and one here, and now they're marked congruent. The other way to see a congruent marking is by using what I just did, but then also putting a line or a dash through that. The advantage to using something like that would just be it tends to be a little bit cleaner if you were referring to multiple congruent angles. So for example, if I wanted to show that none of these angles are congruent, I might want to show it with all different markings, similar to the idea of congruent sides that were not always congruent. They have to match. So if this top one was not congruent, but yet these two base angles are congruent, I can mark them so the doubles would match the doubles. Now this would be no different than if you were to do multiple loops. So that's a single, that's a double, that's a double. These two, angle A and angle B, are congruent, but not with angle C. Okay, another idea that shouldn't be too hard to understand is an angle bisector. So we already understand the idea of what a bisector would be. A bisector cuts something into two congruent parts. An angle bisector is going to split an angle to two congruent angles. An angle bisector is commonly a ray, but it can also be a line. So as it shows right now, I am not totally sure if ray UT is an angle bisector. But if I was to show that angle STU is congruent to angle VTU, then I would know that ray TU would be an angle bisector. So angle STU congruent to angle VTU, then ray TU is an angle bisector. Okay, actually I want to take a second and take a look at this angle and how I named it. So I said that angle STU is congruent to angle VTU, which is correct ways of naming this angle. But I want to talk about why I cannot just call it angle T. So because I have a vertex of T here, okay, and an angle is named by a vertex of T, you would commonly see students call this angle here in yellow angle T, which is incorrect. You cannot refer to it as angle T despite the fact that that is a vertex. The reason being is because T, that vertex, belongs to more than one angle. So if you were to say angle T, I don't know if you're talking about STU. I don't know if you're talking about VTU. Or for that matter, you can also be talking about this entire big angle here, STV. So what I always like to constantly remind you guys is that I would always, when possible, name an angle with the three letters, with the vertex being in the center. This will avoid any time that you can't use just a single vertex letter. Okay, so let's talk about adjacent angles. So adjacent angles are two angles that lie in the same plane, but they have to have a common vertex and a common side. So I have quite a few different angles going on here. I have some that are adjacent and some that are not. So let's talk about angle 1, angle 2, and angle 3. Angle 1 and angle 2 would be adjacent angles. Okay, the reason I know that is because they share a side. They share ray SN, and they also share a vertex S. But you should notice that angle 3 also has that same common vertex S. However, angle 1 and angle 3 are not adjacent. And the reason that they are not adjacent, despite the fact that they do share a vertex, is they don't share any common sides. So notice that the rays that are needed to create angle 1 are OS, or SO and SN, but the rays needed for angle 3 are I guess that's an I, SI, and SD. So they do not share a common side. So 1 and 3 are not adjacent, 1 and 2 are adjacent. So then let's take a look at the other combination, which would be angle 2 and angle 3. Now, angle 2 and angle 3 for sure have a vertex S, okay, and they do share a side SI. So, because angle 2 is made up of ray SN and SI, and angle 3 is made up of SD and SI, they do have a side in common. They have a common vertex, so angle 1 and angle 2 and angle 3 are also a pair of adjacent angles. Okay, so finishing up, we got two more parallel and perpendicular lines. Words that you have probably seen before. You may not remember it, but you have done it in Algebra 1. So parallel lines are two or more lines that are always the same distance apart, and they will never ever touch. Any two parallel lines must always lie in the same plane. We do mark a diagram that has parallel lines, and we'll also notate it with parallel symbols. So I have two sets of parallel lines here. So I would show that AB is parallel to CD by simply putting a bit of an arrow kind of throughout the lines. I would write a statement that lines AB is parallel to line CD. So your symbol for parallel lines are just two kind of slanted lines in between the two parallels. So now I have another A, B, and C, D. Perhaps I should have picked different letters. If I wanted to show that these two were parallel, I would mark them with these arrows somewhere in it. But these two pairs are clearly not parallel. They would meet. So I would have to show them a little bit different. So just the same as congruent markings work, parallel markings work the same. So a single would match a single, and a doubles would match doubles. So now I could say on this one that AB is parallel to CD. And finally, our perpendicular lines, which are quite different than parallels because they will definitely intersect. And specifically, they will intersect at a perfect 90. So at perfect right angles. So they're two lines or two rays or two segments or one line and one segment or any combination that meet exactly at 90 degrees. You don't have a separate marking for perpendicular because they meet at 90 degrees. You're just going to use that perfect corner marking again to show that. There is a symbol for perpendicular. It looks pretty much like two perpendicular lines. So here I would want to write a statement like AB is perpendicular to CD. Okay, or perhaps for this one, segment A and B is perpendicular to segment NM. And that is it for our vocab on our building blocks angles.